Welcome, everybody. I hope you can hear me. Today, I will talk about ultra-short pulse laser micromachining, about scale-up strategies for high throughput. But let me spend first a few words about the Swiss Photonics network. Is, as you said before, this is a national thematic network and innovation booster for photonics. From research and industry, our mission is to improve the competitiveness of its members, or of our members, through the support of innovation forces. We have so-called national labs. This is a coordination function. We organize events, workshops, we do some networking, and since a short time ago, we can also fund the start from innovation projects, but only very small. Then the Swiss Society of Optics and Microscopy. This is a society representing Switzerland in international organizations, also including microscopy, and is the member of both Swiss Academies of Science. And now to my person, myself, I'm a professor at the Bern University of Applied Sciences. This is one of the 8 Swiss universities of applied sciences. We have a very practice-oriented education and research. We have many industrial collaborations, and I'm representing here the Institute of Applied Photonics and Surface, Laser Photonics and Surface Technologies. So, as you may know, Switzerland is well known for micromachining, like watches and so on. That's why I'm talking today about this topic. It is rather a scientific, technical talk. I hope it's not misplaced here, but I think it would work. So if you have a short look at the industrial ultra-short pulsed lasers, you can see here, this is not exhaustive. These are just 3 examples. You will get average powers today, industrial ready, of several 100 watts. If you go to more research, you see the average power is increasing, and recently 3.5 kilowatts of ultra-fast pulsed lasers have been proved. And this is the pulse duration of 430 femtoseconds. This is really impressive. So if you do a very short summary just of these 2 slides, we can say industry-ready lasers with more than 100 watt of average powers are available today for ultra-short pulses for micromachining. Multiple 100 watt average power will be industry-ready soon. 1 kilowatt is on the way, and indeed, missing average power will not be an issue in future, I guess. So the important question will be, how can we deal with these high powers? And that's what I want to talk today about. Let's start with a simple example. Let's just machine a square. And this is mostly done with the Galvo-Scanner, with the hatching. You go forth and back, switch on laser off and laser on and off. And if you can synchronize everything, you have control about the spot positions. You will see later why this is important for us. So then you choose the laser parameters like pulse duration, wavelength, spot size, repetition rate. You can also use the burst mode. I will speak later about this. And you can set the spot-to-spot distance by the scan speed and the line-to-line distance. And then you machine squares with the given side lengths, with the number of layers into the material you want to investigate. Mostly we, just for our studies, we select a fixed number of pulses per area, which means the number of layers depends on the distance between the spots and the number of pulses per burst and so on. And then we machine several layers with increasing average powers because we want to see how we can scale up our processes from the threshold up to several watts, or in terms of the fluence, which is the pulse energy per area, from the threshold up to several joule per square centimeter. We measure the depths of the squares. Of course, the volume, removed volume, is the size of the square multiplied by the depth. We can calculate the effective laser runtime from the parameters we defined before, and from this we can then calculate the removal rate of removed volume per time. So, and you see here an example in silver, just with 200 kilohertz repetition rate, 10 picosecond pulse duration. And you see, indeed, the removal rate is increasing with average power, and with about 15 watts, a little bit less, we can remove about 2.5 square millimeters per minute. So mostly we then divide our removal rate by the average power to define somehow an efficiency, how much removal rate we have per average power, or what volume can we remove per energy we put in. And then you end up in this kind of curves. And then you, if you put it into this value of cubic micrometers per microjoule, volume per energy, you see it, and then you can see you have here optimum point, an optimum fluence, pulse energy per unit area, and then you have here maximum specific removal rate. And this is the optimum point where you can use most part of your energy. So this is true for many metals. You see here 3 different metals: brass, copper, gold, and every metal follows this trend, and you can have already also a scientific model to fit in. I will not explain the model, but what you should see here is, I mean, this is 10 picoseconds, 200 kilohertz, this optimum point with the spot size of 16 micrometer radius about, which is typical for microprocessing, maybe already a little bit high. You see the average power you can use in this case is fairly low, about 2 watts. So we have to think about to scale this up. What can you do? Now you can say, okay, I work faster, higher repetition rate, higher speeds. If you want to keep the pulse overlap, you have to increase the speed. So let's make 2 examples. Here we are working on copper, maybe with 50 watts or with 100 watts. We check between overlap of 75% and 50%, and we end up in a speed of 50 to 150 meters per second. So when you go to steel, make the same calculation, maybe you increase a little bit the beam size, then 75% overlap ends up in 100 meters per second, and when you go to 50% overlap and 100 watt, you need more than 400 meters per second. So this means working near the optimum point for metals with a few 10 watts of average power demands high marking speeds of 100 meters per second and more, and which is not accessible via Galvo-scanners. You need single pulse switching at repetition rates of a few megahertz to about 20 megahertz, and this is hard. So what can you do? You can go to polygon line scanners. You see here just 2 examples. You replace your standard Galvo-scanner with the turning polygon mirror, and then you can work with speeds up to 100 meters per second easily. You see here a topography of Switzerland, machined in steel with the repetition rate of 4 megahertz, an average power of 26 watts. Beam size was 29 micrometer in radius, and results are pretty high. It works. We tested this up to 6.8 megahertz repetition rate, average power of 40 watts. The limit there was not the process, it was the laser. You could not switch on single pulses at this high repetition rate. But anyway, the question is now, can you further scale up to several 100 watts? There are 2 problems which can occur. If you have a pulse beam moving along a straight line, you ablate material, and then the next laser pulse can maybe exactly go into the plume, and so this plume can shield the consecutive pulses. This is called shielding, particle or plasma shielding. And another effect is the heat accumulation. You always have a fraction of the incoming energy which is converted to heat. Even it's ablation, it's ultra short pulse, at least 30% will be resume in the material. So and now we have an overlapping beams, and you have temperature distribution, and this can accumulate and the material become very hot. So we made some experiments with the very high speed polygon scanner, high power ultra short pulse lasers. You see here the results for copper. Again, we have this specific removal rate, removed volume per energy as a function of the fluence, and you see highest values you achieve with 200 kilohertz repetition rate, and here you see when you go to 10 megahertz repetition rate, it drops down by about 30%. You see here the maximum values we have obtained. we can also go up to 40 megahertz, which is not plotted here. Then you are somewhere be less half of the one you get with 200 kilohertz. And this is shielding. So shielding will really occur in case of copper and also brass and others. But anyway, we could demonstrate that we can machine with 300 watt of average powers, 3 picosecond pulses, and have a removal rate of about 40 cubic millimeters per minute. But this scale-up process, you see, is limited by plasma shielding. I think much more than 300 watt is not possible in this case. When you go to steel, the drop in the removal rate, when you increase the repetition rate, you see you go here to 40 megahertz, is much less pronounced. This works. You have a drop of 15% between, let's say, 8 megahertz and 40 megahertz. That's okay. But what you will see is a very bumpy surface. When you go to the result with 10 megahertz, which was here, you see a bumpy surface. And when you go to 40 megahertz, it's even more pronounced. And this is heat accumulation. This is now due to heat accumulation, which will reduce the quality of the machining process. So what can you do? In principle, you can say, okay, a given spot pattern I have here, I can also machine this in n passes with n times larger pulse-to-pulse distance. Let's say here in 2 passes, same picture, or in 4 passes. Then you have more distance between the single pulses and you have less problems with shielding and accumulation. We have shown this here on steel with an average power of 40 watts. This is just a surface machined with 25 meters per second speed, and distance from pulse to pulse was 3 micrometers. We machined 30 slices. And then we made exactly the same with 100 meters per second. The pitch from pulse to pulse was 4 times higher. But then we need also 120 slices. But finally, it works. This so-called interlaced principle could work, and you could machine then with very high quality. But now calculating this for several 100 watts of average power with the normal average, with the normal beam size of 15 micrometer radius, and let's take spot to spot, diameter of a spot as spot to spot distance, then you will end up in a repetition rate of 48 megahertz for 100 watt in steel, or already 240 megahertz with 500 watt in steel, and then the marking speed would be 8,000 meters per second. That's really high. If you go to copper, this is a little bit less demanding, but anyway, you will end up in marking speeds of 1,650 meters per second for 500 watts. This is today maybe the limit which could be possible with the polygon, but in copper you can also go to a little bit higher pulse energies. You will be then a little bit less efficient, but anyway it works, and then you end in these values here. So we can say maybe it would be possible to machine copper with several 100 watts of average power, but anyway we need alternative approaches. And this is now the second part. We have just discussed this fast scanning. So this is really a hard topic, but you can also go to other strategies. You can use pulse burst. This is multiple strategies. You have several very small pulses in very short distance, and then you move, and then you have again a burst of pulses. You go from this single pulse situation to the burst, or you can also make a multi-spot strategies in space. You can say, okay, I don't work with only one spot, I work maybe with 4 spots, make this kind. And there is also a third possibility. If you generate patterns with single pulses, maybe you generate this pattern here. We can also try to form this directly with the spatial light modulator or diffractive optical elements. So let's first talk about bursts. You see here, again, the specific removal rate as a function of the pulse energy per area for different number of pulses per burst, starting at single pulses, going to 8 pulses per burst. The time distance between the single pulses in the burst is 12 nanoseconds, and then you see, okay, you drop a little bit in the specific removal rate, but the drop is not very high, that's okay. And if you go to high fluences, you have even a benefit from the burst. You are more efficient than with single pulses, but you will never reach the efficiency of a single pulse at its optimum point. But you have to have in mind that for an end pulse burst at identical pulse energy per area and the repetition rate, the average power you can work with is n times higher. And therefore we can say, okay, in case of steels, bursts can really help to work with higher average powers and can support our scale-up process. It works, you see here, a honeycomb structure machined in a steel roller, and this is also 4-pulse burst. This works very well. If you go to copper, again with bursts, we have a quite strange behavior. This is a single pulse. Again, the efficiency as a function of the pulse energy per area. You go to 2 pulses, then you drop below 50% of the efficiency, which means you have a radar position. You go to 3 pulses, you even increase the efficiency of a single pulse. You go to 4 pulses, you drop down again. You go to 5 pulses, then you are again up. So this is a little bit of strange behavior. It's explained. I don't want to spend too much words about this. Just to say, this is a typical behavior. It's also found for aluminum, silver, gold, and brass, and so on. And just to say, if you want to work with bursts, please use an odd number of pulses per burst, which means 3 or 5 or 7, but not an even, not 2 or 4. So this is working, and now we can go to another strategy, multi-pulse processing. You combine a beam splitting unit with the scanner. You just see here an example how this works. So, and this is a way to work. You see here a picture, but it's of course restricted to periodical structures. But anyway, it's a good idea. I can show you here the results of a similar setup I have shown before, realized with the diffractive optical element. And we will now stamp multi-spot patterns with equally spaced spots. You can move the pattern, you see here 5 by 5 spots, just by 1 spot to spot distance between 2 laser pulses. So, and then you make always with 1 laser pulse 25 spots, and then you move. And if you have a synchronized scanning, that's what I have shown you just at the beginning, then you are able to hit absolutely the same positions in the next and then the next layer. So you can realize a multi-pulse drilling on the fly process, and you see here the result. This is left a single spot, just 1 spot per pulse. Then you can use 640 milliwatts of average powers with need more than 675 repetitions. And when you change to 5 by 5 spots with the diffractive optical elements, you can go to 16 watt average power. You reduce your repetitions to 27. And you see here the process. And after 6 seconds, or about 6 seconds, the holes with the 5 by 5 spot are drilled. And you need with 1 spot 150 seconds. And if you calculate, you have here 75 holes per second in this case, 1700 holes per second here. And when you go to even higher number of holes, you can increase the drilling rate to several thousand holes per second. This is just showing you that this multi-spot strategy holds. You see here the result of the drilled foil, the entrance just cleaned by an ultrasonic bath, good quality, and there is no difference in this case between the 2 technologies. So now let's go to beam forming. Beam forming can be done, for example, with the spatial light modulator. You add this here, you calculate the hologram, and then you get in your focal plane a special pattern, like here a ring or a square or a triangle, and then you can work. And the only problem you have is that the spatial light modulator is a phase-only device, so you will always have some speckles, but anyway, it works. Here is the setup we have used. This is a unit from a company which goes up to maximum laser power of about 100 watt. The field size you can work is 4.4 millimeter. You have a software to calculate the holograms. And we just made a very simple example. We stamped the ring, not a spot, the ring. And for every position, we could stamp a ring. And if you switch on and off the laser in the right case, you can generate forth and back this Olympia logo pattern. Olympia will be next year, right near to you in Tokyo. So that's what we have done. And you see here how this works. These are rings, and when you go further, this is how the pattern looks like, good quality. So this idea of stamping is working. And this now you can also think bigger to a regular pattern. You see here a special pattern which has a elementary cell, this one here, and you can try to generate this elementary cell not only by an SLM, also by a diffractive optical element, which is a higher quality, of course. You need a gauge system to adjust the correct DOE size so that you have exactly the good size in your focal plane. You need, of course, a good beam quality, a Gaussian beam for the correct structure, but a Gaussian beam is mostly emitted by an ultra-short pulse laser, also for high average power. And then you can structure. And you can stitch this with the synchronized Galvo-Scanner. This represents the positions of the scanner when the laser pulse is shot. And then you have just to adjust the distance of spot to spot and line to line. And then you can machine regular patterns. So, and if everything is correctly adjusted, also multiple elementary cells can be created by a DOE. You see here in examples with 3 cells in the first line. You can move by 1 elementary cell from pulse to pulse, but you have 3 cells. And you can even go to higher number. I will show you a 3 by 3 and also use the burst mode. And then you are able to work with really high pulse energies, high number of elementary cells in 1 pulse, and also with pulse burst. And in this way, you can really scale up your process. We have tried this with the other pattern. I'm not allowed to show you this here, but in principle, this is a way to scale up. So let me now conclude. We have seen that the single beams with low pulse energy, we can use polygon scanners to achieve high marking speeds. We could demonstrate scale up, but this is limited by heat accumulation shielding effects, and even higher marking speed with synchronization would be needed to further scale up. We can work with high pulse energies. We can use multispot strategies with DOE and scanner, which can be applied for periodic structures. We have a little bit more flexibility with the spatial light modulator, but this one is limited in the laser power. And a beamforming element, DOE, or also an SLM, allows efficient use of high pulse energy and therefore enables scale-up processes. And to my opinion, the combination of beamforming elements with conventional scanning devices is a promising approach to really work with several 100 watt of average power, which will be available in the near future. So with this, I will end my talk, and thank you very much for your kind attention. Thank you.